All right, next I'll talk about change of variables for double integrals, as well as the Jacobian matrix, which is related to this. So the background is that sometimes we'll need to change the variables or the coordinate system that we're working in for an integral. Otherwise, the technicalities of and the mechanics of doing the integration just becomes too difficult and complicated. So one common instance of this is if we want to convert from an XY Cartesian system to a polar system that uses, R for radius and then theta for the angle instead. So the main hassle in doing a change of variables is changing the differentials at the end. In other words, the dy dx or the dx dy, it doesn't matter which order. Okay, so basically there's a formula that you use to replace these old differentials with the absolute magnitude of the determinant of something called the Jacobian matrix, which is going to be multiplied, and I'm saying that in quotes, by dr d theta, which are the new variables. So to form this Jacobian matrix, take whatever equation you have for converting the variables. So for example, in this case, we would have x equals r cosine theta and y equals sine theta. R sine theta. That's just a standard, well-known conversion to polar coordinates. So now you take the derivative of x with regards to r in the upper left corner, and you take the derivative of x with respect to theta in the upper right corner, the derivative of y with respect to r in the bottom left corner, and the derivative of y with respect to theta in the bottom right corner. So in this example, each of those four derivative terms have the old variable on the top and the new variable on the bottom in the denominator. But this doesn't have to be the case. So if you had a conversion formula where the new variable was isolated and defined in terms of the old variable, which is the opposite of that example I just gave, with x equals r cosine theta, etc., then you could use that to take the derivative, and you would have the new variable in the numerator and the old variable in the denominator for this Jacobian matrix. So again, what you do is you form the matrix as I just described, then take the determinant of it, which is just where you multiply the diagonal terms and then subtract the second set from the first set, and then take the absolute value of that. So in other words, you can't have a negative answer come out of this thing. And then put that value along with the differentials of the new variables in the place of the differentials of the old variables. So again, this is where I said multiplied earlier, in air quotes, because you're not really multiplying it by differentials, you're just sort of writing them next to each other. So another thing to do, which is easier, is that we need to change the variables, not just of what comes at the very end of the integrand, but we actually need to change the variables of the function that was originally inside the integrand. So you do that, that's fairly easy. Just use the formula that we already discussed, which is any place where you have x will become r cosine theta and y would become r sine theta, or whatever the formula is. All right, so now let's talk about double integrals and polar coordinates. This is basically just an example of what we just discussed. So it's done by a simple formula, which is just to replace dx dy with r dr d theta. So in other words, this r is simply what we get as the answer once we do all that, Jacobian matrix stuff for the polar coordinates.